Good morning. This class we are discussing another rearrangement, that is Fry's rearrangement. Fry's rearrangement. In Fry's rearrangement, phenyl esters on treatment with anhydrous aluminum chloride will undergo a rearrangement and will give ortho and para acylated phenols. What is that? When phenyl esters. So, what is Fry's rearrangement? When phenyl esters treated with anhydrous aluminum chloride AlCl3 will undergo a rearrangement to give ortho and para acylated phenols. Okay, so keep it in mind, when phenyl esters treated with anhydrous aluminum chloride will undergo a rearrangement to give ortho and para acylated phenols. So keep it in mind, what is phenyl esters? What is ester? R, C, double bond, O, R. This is ester. Phenyl ester means here it is phenyl group, or here you can say that here it is benzene ring. Okay, this is phenyl ester. So this is phenyl ester, and treated with anhydrous AlCl3 will give ortho and para acylated phenols. Okay, look at here. So Fry's rearrangement, when phenyl esters, how will you write phenyl esters? Look at here. Okay, O, C, double bond O, CH3. This is an example for phenyl ester. What is this one? Phenyl acetate. So this is phenyl acetate. Okay, phenyl CH3CO group, phenyl acetate. Phenyl acetate is treated with anhydrous AlCl3. Of course, heating is required. Anhydrous AlCl3, and what we get? We get ortho and para acylated phenol. Acyl group. Here it will come COCH3. This means ortho acylated phenol, and we get para acylated phenol. That means in the para position COCH3. So acyl group is coming ortho to the hydroxyl group and para to the hydroxyl group. This type of rearrangement is known as Fry's rearrangement. So what is that? Phenyl esters when treated with anhydrous aluminum chloride will undergo a rearrangement to give ortho acylated phenol and para acylated phenol. What is this one? This compound is ortho hydroxy acetophenol. Ortho hydroxy acetophenol. Ortho hydroxy. What is this one? C6H5COCH3 acetophenol. Okay, acetophenol and para hydroxy acetophenol. That means hydroxy compounds of aromatic ketone. Hydroxy compounds of aromatic ketone. Okay. That is what is formed. That is ortho hydroxy acetophenol and para hydroxy acetophenol. Okay, hey, look at it here. Here you can see that there is a migration of a group. So COCH3 acyl group migrated from oxygen to carbon. Oxygen from oxygen group. COCH3 group is migrated from oxygen to carbon, or it is migrated from oxygen to para carbon. That means here you can say that this type of oxygen to carbon migration. Oxygen to carbon migration of what type of group? COCH3. Okay, this group is migrating from this oxygen to carbon. So this is a case of oxygen to carbon migration. So look at the reaction and let us go through the mechanism of Fry's rearrangement. Okay. So we start with okay, here it is OCOCH3 RCOOR, but this is phenyl group. So phenyl acetate, this is phenyl acetate. Phenyl acetate, this is a phenyl ester. Okay, phenyl ester acetate. Okay, when treated with AlCl3, AlCl3. Okay, now listen the mechanism. We know that here is a lone pair of electron. Lone pair electron is there in the oxygen atom. That means phenyl acetate, phenyl ester. This ester can act as Lewis base. Phenyl acetate can act as a Lewis base because it can donate a pair of electrons, so it can act as a Lewis base. And you come to AlCl3. Now this AlCl3, since alumina is having vacant orbitals, it can accept a pair of electrons. That means AlCl3 is acting as a Lewis acid. Why AlCl3 is acting as a Lewis acid? Due to the presence of vacant orbital in aluminium. And second reason, you can see that the central metal atom is attached to electronegative chlorine atom. Therefore, this Al will become more electropositive. These are the two reasons why it is acting as a Lewis acid. One reason, it has vacant orbital, therefore it will accept a pair of electron, this central aluminium atom. And second reason, this aluminium is attached to electronegative chlorine atom, therefore aluminium will have more positive charge. Therefore this is acting as a Lewis acid. Lewis acid. Okay, AlCl3 is acting as a Lewis acid, and what it will form? You look at it here. Okay, here it is like this. Okay, and here you can see that O. What is that? Here it is COCH3, and this O is attached to what is that? AlCl3. Since a pair of electron is donated, oxygen is getting a positive charge, and this part is negatively charged. Okay, AlCl3 minus. This is very clear. Oxygen is donating a pair of electrons, so oxygen is positively charged, and this part AlCl3 minus. Okay, it is clear. Now we can see that for stability, what will happen? This bond, this COCH3 bond, this bond breaks. Okay, and this bond breaks, and what do we get? We get a structure like this. It is like this. What do we get? Look at it here. Here it is. Okay, here now change. Okay, ring is here, and here it will become O and AlCl3 minus. Okay, AlCl3 minus. Okay, AlCl3 minus, and this part is okay. Oxygen no more have positive charge, and AlCl3 minus plus what will form? Since the bond is breaking from this carbon, we get C double bond or CH3, and it is having, of course, it is having a positive charge. The carbon is having a positive charge, and this cation is known as acylium cation. Acylium cation. This acylium cation is acting as an electrophile. Okay, look at here now. This is important because the next step is starting with the acylium cation. Look at it here. Since this bond is breaking from this carbon, carbon is getting a positive charge, then this is a cation. This is a cation. What is the driving force of breaking this bond, or why this acylium cation is separating? You can see that why this is separating means this acylium cation can be stabilized by resonance. That is the reason why this bond is immediately breaking, because after breaking this bond, the acylium cation is forming, and that acylium cation can be stabilized by resonance. What is the resonance structure? Look at it here. You can see that this is CH3, C double bond O. Of course, here is a positive charge. How it is resonance stabilizing? Look at it here. This lone pair of electron in the oxygen atom, this will be shifted to here. Okay, and what will form? You will get another structure like this. Okay, so it is like this: CH3, C triple bond O with a positive charge. This way, this acylium cation cation can be stabilized. Look at it here. This lone pair electron is shifting to here. Therefore, the positive charge on the carbon atom is removed, and you get a positive charge on the next step. Again, this will go back again. That means this is acylium cation can be stabilized by resonance. That is the reason why this bond is breaking, because after breaking, this acylium cation is forming and it can be stabilized by resonance. So this is the first step, or not first step. This is the beginning part of this mechanism. First, acylium cation is forming. Okay. Now look, we are continuing. So this is very clear. Since this is acting as a Lewis base, AlCl3 is acting as Lewis acid due to the presence of vacant orbital as well as more positive aluminum atom, and we get a structure like this. And after that, acylium cation is forming. That acylium cation is stabilized by resonance. So now what we are getting, look at it here, and see, here it is like this, O, and what is that, AlCl3 minus, okay, AlCl3 minus. Now our acylium cation, look at it here, C double bond O, CH3, C double bond O, CH3, positive charge. Now this acylium cation can act as an electrophile. This is acting as an electrophile, and as we studied earlier, what type of reaction will occur now? This electrophilic addition, that means this bond breaks, this bond, you can see that this bond breaks from this carbon, okay, and it is attaching to acylium cation, because acylium cation is acting as an electrophile. The bond breaks and it is joining with this one, and what we get? We get a structure like this. Okay, here it is like this. Okay, now it is like this, and the bond is joining with C double bond of CH3, and you can see that here it is O and AlCl3 minus, and here it is a positive charge. Here it is a positive charge. Okay, and you can see that when a positive charge is created here, you can see that this lone pair of electron present on the oxygen will be shifted to here. Okay, and what do we get? Look at it here. Okay, we are getting a structure like this. Okay, here it is like this. Okay, C double bond O CH3, C double bond O CH3, and here it is double bond O and AlCl3 minus. Of course, oxygen is getting a positive charge. In the next step, what will happen? Since oxygen is getting a positive charge, this bond, this AlCl3 bond breaks, and the pair of electron is coming back to oxygen, and we get a structure like this. Okay, look at it here, and we are getting double bond O, and here it is like this, and here it is C double bond O CH3. Okay, and what is eliminated? Minus AlCl3. AlCl3 is removed because this bond is breaking, and a bond pair electron is migrating to oxygen, and we get a structure like this. In the next step, you can see that there is a tautomerism. Look at it here carefully, and here you know that here is a hydrogen. Okay, or you can say that for regain the stability or regain the aromaticity, what will happen? This is a type of tautomerism. This bond is shifting to here, and this bond is going to moving to oxygen, and what will happen? That means minus H plus and plus H plus H plus means this oxygen, negatively charged oxygen, will take this proton, and what we get what a structure like here. It will become a double bond, and here it will become OH, and here it is CH3. Actually, what type of this one? 1,3 tautomerism. 1, 2, 3. 1, 2, 3. 1, 3 tautomerism. By 1, 3 tautomerism, the ring is getting its aromaticity, and you get what is that? Orthohydroxyacetophenone. Okay, here it is. I am starting with this step. Okay. Okay. O AlCl3 minus. Okay, and now our acylium cation. What is acylium cation? COCH3 plus COCH3 plus. Now you can see that okay, Okay, you take this bond. Okay. Now you can see that this bond is breaking and joining with okay. And what we get, look at it here. Okay, here it is like this. Okay, and you can see that here it is like this, and here it is what is that C double bond or C double bond or CH3, C double bond or CH3, and here it is a positive charge, and here it is O AlCl3 AlCl3 minus. Okay, AlCl3 minus. And in the next step you can see that this bond is migrating to here, and we get okay, here it is like this. Okay, here it is C double bond O CH3, and here is double bond, here is double bond, here it is O AlCl3 minus, and here is a positive charge, and we have discussed earlier this pair of electron is shifting to here, and what do we get? We get structure like this. Okay, look at it here. Okay, here it is like this, and okay, double bond O AlCl3 minus, and this is positive, and here it is C double bond O CH3, C double bond O CH3. In the next step, this bond breaks from AlCl3, and one pair electron is shifting to oxygen. We get a structure like this. Here is double bond O, and minus AlCl3. AlCl3 is removed, and here it is C double bond O CH3. Okay, now in the next step, what is happening? You can see that look at it here. Here is a hydrogen. Here is a hydrogen for resonance stabilization. This bond is shifting to here. Okay, and what will happen to this bond? This bond will be shifted to here, and what will happen to one of the double bonds? This is moving to oxygen, and what will happen? This proton removed is attaching to oxygen. That means minus H plus and plus H plus. What do we get? We get our compound like this. Here it is double bond, here it is double bond, and here it is COCH3, and here it is OH. What is this one? Orthohydroxy acetophenone. So we get para-hydroxy acetophenone, and we get ortho and para-acylated phenols. This is what is Fry's rearrangement. So Fry's rearrangement is important for the preparation of hydroxy aromatic ketone. Hydroxy aromatic ketones, that type of ketones cannot be simply prepared by simple acylation of phenol. That means simple acylation of phenol. This type of compounds cannot be prepared. Therefore, this Fry's rearrangement is important. Now look at it here. Why this Fry's rearrangement is important? We can discuss with an example. This Fry's rearrangement is important for the preparation of adrenaline. Which is a heart stimulant. Okay. So for the preparation of adrenaline, this Fry's rearrangement is important. Let us go through how adrenaline is prepared. Adrenaline is a heart stimulant. Okay. So adrenaline. Okay, look at here. Okay, we start with catechol. Okay, OH, catechol. Okay, catechol is treated with Cl, CH2, CO, Cl, CH2, CO, Cl. That means CH3COCl is acetyl chloride. This means chloroacetyl chloride, because if it is CH3, what is that? CH3COCl is acetyl chloride. One of the hydrogen atom is replaced by a halogen. So halogenated acetyl chloride Cl, CH2, COCl, when treated with catechol, you can see that okay, I am taking this H and Cl. HCl will be removed, and the mechanism is simple, because this lone pair of electron will attack on this positively charged carbon, then that time this bond will be migrated to oxygen, and you can see that and oxygen is here. When it is attaching, oxygen is getting a positive charge. For stability it will remove H plus, and okay, that part is over. And when the bond is shifted to here, it will become a minus charge. When it comes back, the Cl minus is removed. That means HCl is removed. Okay, and what do we get? Okay, I am telling HCl is removed. What do we get? We get a structure like this. Okay, here it is like this, and here it is OH, and what is here? Here it is what is that? O. What is that? C double bond O. CH2Cl, or C double bond O, that means minus HCl. Look at it here, this Cl and HCl is removed, and what is happening? O is joined with COCH2Cl, or COCH2Cl, and in the next step, what is happening? Actually, this is our phenyl ester. This is type of phenyl ester. Okay, and in the next step, it is treated with our anhydrous AlCl3, with heating, or you can use pyridine. Okay, pyridine in presence of pyridine. Okay, what do we get? We get a structure like this. Okay, pyridine, and we get a structure like this. Okay, here it is like this. Okay, and here it is. Okay, here it is OH, and here you can see that O and C double bond O, CH2Cl. As we have discussed, this lone pair of electron will attack on the vacant orbital of Al, and it will join with AlCl3. AlCl3 is acting as a Lewis acid. This is acting as a Lewis base. It is donating a pair of electron. Definitely you will get a positive charge, and this is getting a negative charge. Okay, and in the next step, we can see that in the next step, what is happening in the next step? Since we have discussed the mechanism, I am directly showing in this structure only. This bond is breaking from this carbon, and it is this bond pair electron is moving to oxygen, and what will form? We get a structure like this. Okay, here it is. Okay, here it is OH, and here you are getting AlCl3 minus, plus what is our cation is forming. Since the bond is breaking from this carbon, we get C double bond O, and here it is CH2 Cl with a positive charge. This is our electrophile. This will act as our electrophile. Okay, it will act as our electrophile. Okay, now in the next step, we are taking this compound. Okay, in the next step, look at it here. Okay, here it is like this. Okay, okay, here it is AlCl3 minus, and here it is OH. Okay, here it is OH, and you can see that here is our electrophile. Electrophile is C double bond or CH2Cl with a positive charge. Okay, that means this is our electrophile. Now you can see that this bond is breaking from this carbon. Okay, and you can see that it is attaching to this electrophile, and we get a structure like this. Look at it here. We get a structure like this. Here it is like this. Okay, AlCl3 minus, and here it is. And what is here in the para position? C double bond O, CH2 Cl. Here it is a positive charge. A positive charge is here. Okay, since the bond is breaking from here, here is a positive charge. Okay, and in the next step, you can see that this is shifting to here. And what do we get? We get a structure like this. Okay, here it is like this. You can look at it here. Okay. That means here, and here it is C double bond O, CH2 Cl. Here is our OH group. Of course, here is our OH group is here. Okay, and here it is O AlCl3 minus. Here it is a positive charge. and in the next step what is happening, this pair of electron is shifting to here, and we get a structure like this. What is that? Here it is okay, here it is double bond, OH is here, and here it is double bond OAlCl3 minus, and here it is oxygen is getting a positive charge, and here it is C double bond O CH2Cl, and in the next step what is that? Minus AlCl3 minus AlCl3 minus AlCl3, and we get a structure like this. Okay, here it is double bond O, and here it is here it is OH, and here it is C double bond O CH2Cl, and in the next step what do we know? As we know that here it is hydrogen. Okay, it is like this. Okay, and what is that? Minus H plus and plus H plus. Okay, minus H plus and plus H plus. But we get a structure like this. Okay, here it is like this, and here is double bond, here is double bond, here is OH, here it is OH, and here it is C double bond O CH2Cl. Okay, now this compound, what is happening in this compound? This one is treated with methylamine CH3NH2. This compound is treated with methylamine. Then what will happen? Okay, this compound is treated with methylamine. Then what is happening? You can see that methylamine, that means CH3NH2 can be written as NHH, and what will eliminate? HCl will be eliminated. Okay, that means so keep it in mind, this compound here we are having this structure, and this compound is treated with methylamine CH3NH2, CH3NHH. HCl will be removed, and what we will get? We get a structure like this. Okay, here it is here it is OH, here it is OH, and you can see that here it will become C double bond O. What is that? CH2NH CH2NH CH3. Okay, this compound is forming, that means CH2, then NH CH3. This on reduction H2 in presence of a catalyst, what will happen? This CO group will be reduced to CHOH. CO group will be reduced to CHOH, and we get a structure like this. Look at it here. Okay, here it is OH, here is also OH, and here you can see that this will be converted as CHOH, and the rest is as it is CH2NH CH3. Okay, this is what is adrenaline. Okay, adrenaline. This is adrenaline, and this is a heart stimulant. Okay, this is one of the applications of Fry's rearrangement. Okay, thank you.